Okay, so this is where we left off today. And Bismillah ar-Rahman ar-Rahim. First of all, this is basically a lecture for tomorrow's our new experiment with the new flip classes. And what we're going to be doing tomorrow, inshallah, we will be looking at analyzing circuits. So we went through today where we talked about resistors, electromotive forces, and electromotive forces with internal resistances with small, which is R. And this can have both ways, which I'll talk about what's meant by positive and negative. And we said the voltmeter and the ammeter will be left for you to do in the lab. Okay, let's start by first we wanted to find this is a circuit, a simple circuit, where we wanted to find the ammeter, the current, and the volt across. So the current and the volt across some points in these two circuits. So first we wanted to find the voltage across this this resistance and internal resistance battery, and the way to do that is by simply, in order to do it mathematically. Now in the lab you just need to connect the the voltmeter across these 2 points A, B, and take the reading. But now mathematically, in order to do that, we wanted to go back to the point where the sum of the volts around a closed loop is equal to 0. Now my closed loop is going to start at some point here. Let's start at some point A, and then it will go all the way, right, and then come back to A, and that will be a closed loop. So if I start there and then I go in here, then I will have first of all a voltage drop here, which is, remember, V is always equal to IR, okay? V is always equal to IR. So that means that in here I have a voltage drop which is equal to minus I multiplied by 4, okay? And then this will not, the ammeter and the voltmeter, as they must have told you in the lab, these guys, they don't have any resistance. So when you add them to the circuit, they're not supposed to affect the circuit. And then I have an increase in the voltage, a voltage gain of 12. So this will be 12 minus 2I, 2I, okay? And then I'm back to point A. Okay, so that means the sum of the voltages now is equal to 0. And as you can see, if I solve for I have 6I goes to the other side, so minus 6I goes to the other side. So 12 divided by 2, so my I is equal to 2 amps. Okay, now if I wanted to calculate the voltage drop across this point, all I have to do is just simply 12 minus 2 times I, which is 2 times 2, which is 4. So 12 minus 2 is 8. So my voltage drop in here, it will be 8 volts. Okay, and if you look, this should be also 8, right? Because if you go from here to here, it's simply the same as going from here to here, because this is nothing, right? It's not going to introduce anything. So since I is equal to 2, 4 times 2 is 8. So V A prime B prime is also equal to 2. So that's the voltage in here. Now if I wanted to calculate, we did that. If I wanted to calculate the current in this resistor, so all I have to do is just look at I and multiply it by any R, and then because this is V is equal to 8, for example, divide by 4 is equal to 2, and that's my current 2. Or I can use this formula here, where the current across the or around the closed loop is equal to 0. Now, rule number 1, which will be it's very important. Rule number 1, which is Kirchhoff's rule, we said that the voltage around the closed loop is equal to 0. So that means if I start at this point here and I go around the circuit this way and come back to the same point, I should get back 0. Okay, let's test that. Now, if we wanted to test that, we first start at this point here. And remember, I'm going to start here and I'm going to gain 12 volts because of the battery. So this is my first gain, 12 volts because of the battery up to here. And then remember, wires are considered to be ideal conductors, so they don't have any they don't introduce any resistance. So this will be constant, and then I will encounter a power dissipation or a voltage drop, and that voltage drop will be simply I. Remember, I is equal to 2. Okay? I times little r, which is 2. So I 2 times 2 is 4. So I drop from 12, 4. So 12 minus 4 is 8. And then, of course, it's going to be constant throughout here. And then once it reaches to this point, it's going to drop again. 4 times 2 is 8. So it's going to drop from 8 back to 0. And as you can see, the rest is 0 because there are no other resistance. And this is what's meant by voltage drop. The sum of the volt, or the sum of the volt, is equal to 0. The voltage drop, or the sum of the volts around the closed loop, is equal to 0, and that's we'll call this Kirchhoff's rule number 1. Okay, we talked about this today in class, and we said that the let me just get the pen again. So these are my definition of the power, and this is how we get it. Okay, and this is another definition of the power, which is P is equal to IV. Let me just write these down because we're going to need them in a minute. V is equal to P is equal to VI or IV, and then it's equal to I square R, or V square over R. Okay, now we wanted to calculate the power output of the battery, of this battery, and the 4 ohm resistor. Okay, this is here. So the battery is comprised of the voltage source, or the EMF source, and an internal resistor, small internal resistor R. Okay, now if you look here, you have this one, you have the volt, right? And current, by the way, is equal to 2 amp, and we said that the current in a closed loop is constant. Okay, so in a closed loop, if you have something like this, the current will be 2 here, will be 2 here, will be 2 everywhere. So that means here I can use the equation where power is equal to E, the voltage, EMF, multiplied by I. So EMF is 12, multiplied by I is 24. Multiplied by 2 is, so that's 24. And then I have a power dissipation here of 2 times I squared. So 2 times 4 is equal to 8. So here you have a power dissipation of 8. And then here you have a power dissipation of 4 times 4 is 16. Remember, 16 power dissipation, so 4 times 4 is 16. That's your power dissipation here. And remember, the voltage drop across these 2 points is equal to V is equal to 8, because that's 12 minus 2 times I, right? 2 times I, 2 times 2 is 4. So the voltage drop will be 12 minus, the voltage across AB will be simply 12 minus 4 is equal to 8, and that's your voltage drop here. If current is I, 2, so that's 16. 16, and this one is also the power dissipation is 4 times 4 is 16. Okay. All right. We also talked about this in class today, and we said that it's simply this simply shows you the definition of the current, except now it identifies something else, which is called time. T is the time interval between 2 events, i.e. between 2 collisions. So it is also referred to as the mean free path. So this is also called, this tau here is also the mean free path. And you can calculate that if you look at tau here. If I give you the density, now we can, the resistivity is this. Right? Please remember this definition. So the resistivity is defined also by E divided by J. Okay? And resistivity is equal to this. Okay? So if I know what the resistivity is, and I know the mass, this is the mass of the electron, which is I know, and Q of the electron is I know, and N is the number of electrons per centimeter cubed. If it's given, then I can calculate the mean free path, which is simply the mean time, or the time between any 2 collisions. Okay, so the points here to remember is J, we know it already, but now we introduced this tau, which is basically the time between two collisions, and we also introduced this formula here where if I know the electric field, I know the electric field, the current density, then I can calculate the resistivity, and the resistivity is also can be given by this equation. Okay, we talked also today about parallel and parallel combination, and this is the series combination. You just simply add, right? And for the parallel combination, you simply have this 1 over R equivalent is equal to that. All right, and we know how we do that, or it's the inverse idea of capacitors. Okay, now if I want to find in here, if I want to find the equivalent resistance, okay, now I is not given here. R, he told this is something that we're going to use from now on. We're going to assume, for simplicity, we're going to assume that all batteries, they have zero internal resistance, which means that it's an ideal battery. It's, in practice, this is not true, or this you can rarely, or you actually rarely find a battery that has zero internal resistance. But for the sake of argument, let's just say that okay, this is going to be zero. If this is true, then what I can do, there are two ways by which I can do this. Let's say find the equivalent resistance. So if I want to find the equivalent resistance, first of all, these two guys are in parallel. So it's 1 over R equivalent is equal to 1 over R1 plus 1 over R2, which is equal 1 over 6 plus 1 over 3. Okay, and then you can do the calculations and you find R equivalent, which is equal to 6. That's 1 plus 2, so 1 plus 2 is 3, and the inverse of that is 3 over 6, so it's 2, right? And then when you combine, so this you're going to have something like this, okay? And this simply the other one, this is the combination of these two. And these guys now are in series, so it will be 4 plus whatever this resistance here, plus whatever this is, and then that will give you the equivalent resistance. Now, what happens if I want, this is another exercise, what happens if I want I? Okay, if I want I, then all I have to do is do my closed loop rule. So I say 18, right, I start at this point here. Okay, and I'm going to loop around, so I'm going to go around like this and come back here. So 18, which is an increase, a voltage increase, and then minus 4. I need to have the equivalent resistance. Okay, so the equivalent resistance will be, I'm going to do this very quickly. 1 over 6 plus 1 over 3, so that will be 1 plus 2 divided by 6. 3 over 6 is 6 over 3, so that's 2. So this is 2. This is 2, and okay, so I can do 4 minus 4i, and then will be minus 2i, because now these guys are simply what? Are simply one resistance, or one resistor, okay? Okay, so that's 6 divided by 18 divided by 6, so I is equal to 3. So my I is equal to 3. Now this is I in here. Now when it comes here, and this is our home, when it comes here, it's going to split or divide it among these two. Right? Now since this is 3 and this is double this, so it's simply saying that 3 will be equal to, now this will be double this because V is equal to IR, and the V's are the same, so the V will be I1, let's call it I1 times 6, and plus 3 times I2. I2, okay, is equal to 0. So that's simply, I'm taking the voltage here across this, and this guy is, so this point here, sorry, at this point here. So voltage here. Okay, so sorry. Yeah, this is I'm taking here the the current at this junction. So the current at this junction is coming in, right? Let's call this, the voltage 18. Sorry, this is messed up. So if I go run, it's 18 minus 4 I1. Okay, I'm going to call this I1. This is I2 and this is I3. So minus 6 I2 minus 3 I3 is equal to 0. Now this equation has 3 unknowns, I1, I2, and I3. So what does that mean? That means I have to analyze this in such a way that this is gone, because what I'm going to do, I'm just going to go start from here and go this way and then go this way. That's one closed loop. That's going to give me equation. Another one is going to go this way and this way, and that is going to give me another loop. So 2 loops, and then I have the junction point, which I'm going to discuss that tomorrow. So you have three equations and 3 unknowns, and you can solve them for I1, I2, and I3. Okay, so this is the let me just do this. Okay, next, so that is clean. Parallel and serial. So now let's look at this. The question says here that which light bulb here, or the combination of these, have higher power output. So higher. So if you look at these one, the combination of these two is 2 plus 2 is 4, right? 4. That means, and the current in this case I have to calculate it. The current will be equal to what? 8 minus 2i minus 4i. So that's minus 2i minus 2i minus 4i. So that means 8 over 4 is the current is equal to 2. So if the combination of these two guys, as we know, is 4, okay, and the current is equal to 2, and the power, as you can see here, is I squared times 2. Okay, so that means 2 squared, which is 4 times 4, is equal to 16. Okay, so the power here, the power output for this combination is 16. However, if you look at this, now this one is 1 over 2 plus 1 over 2, which is a half plus a half is 1. And then the current is 1, the equivalent resistance is 1, and the current is still 2 amp. Oh no, this is he changed it to 2. I total is equal to 2i. Okay, so then you look at this and again calculate I, and after you calculate I, you multiply it by I square R, and then you can compare the two voltages. Okay, now let's look at very quickly at Kirchhoff's rules. Kirchhoff's rules, we have 2 rules. First one, the junction rule, which says that at any junction, first of all, a junction is a point where 3 or more conductors meet. So this is a junction, okay? This is a junction, okay? And that's it. So this one is one current. So this one, we have one current, another current, and a third current. So these guys, 3 or more meet. So these two, this is a junction, and this is a junction. And a loop is any closed conducting path. So this is a loop, okay? This is a loop, yeah? And this is a loop. So any closed conducting path, that's a loop, okay? And the second Kirchhoff's rule, so the first rule is that the sum of i's at any junction is equal to 0. So in this case here will be I1 plus I2 is equal to I3. Okay, this is in, and this is out. So these two add because they're in. There's another way of writing this is the sum of i's in, okay, is equal to the sum of i's out. Yeah. The loop rule is that the algebraic sum, and the algebraic means that you add and subtract. That's what I mean. You have negative and is equal to 0. The sum of the voltages around a closed loop is equal to 0. So you pick any closed loop in here. So for example, if you pick this closed loop here, that the sum, if you start at point F and you go all the way around back to F, that will give you the sum of the voltages equal to 0. Similarly, if you pick this loop, that will give you also 0. So these are the two what's so-called Kirchhoff's rules. Now we have to be careful with the signs when we apply the Kirchhoff rules. So when you go from positive to negative for a battery, when you go from negative to positive, it's plus. So that means the potential has increased. If you go the reverse, so if you travel opposite, then that means the potential is decreased. If I is this way and you travel this way, then this is plus potential. If you're traveling along, so your direction is along the direction of I, then that's a voltage drop. These will become easy once we start doing the applications. Okay, so let's look at some applications here. Find the current in each of the resistors in this circuit. Okay, so the way I do it, I just apply Kirchhoff's rule. So if I start at point B and then I go around like this and then I come back to point B, then the sum of the volts, the potential difference is equal to 0. Let's start here. Now remember, I'm moving this way. That's my direction of motion. If I go from negative to positive, that's an increase or a positive 12. And then I'm going the same direction as the current, and I'm encountering a small resistance. So that will be 2I. That's a voltage drop. Okay? And then when I go around, that will again be a voltage drop, 3 and multiplied by I. Remember, in the same loop, the current is constant. This is I. Okay? And then I'm encountering another one here, which I'm going to remember opposite to again along with the direction of the current. So that will be again 4I. Now look at this. This one I'm going from positive to negative. This one I'm going from negative to positive. So that was an increase. So this will be a drop. So that's minus 4 is equal to 0. And then from here I solve the equation. The only thing I don't have is this I can solve it, and from there I get the current. Once I get the current, I have the resistors, and I can find the voltage any way I want. Okay, that's it. Now let's look at this one here. This one is a little bit, this is something that you will see in the test on Thursday. Okay, now what does he want? He wants the internal. He wants you to find the resistance, the small resistance R. This small resistance here, R, and then he also wants you to find this here. Now, and the current I, he wants also to find the current I. So there are 3 unknowns in this circuit. Now, remember what we said. We said that the purpose of circuit analysis is to find all the parameters for each resistor. That means we want to find R, the value of R, the value of current, and of course all the electromotive forces of the power supplies that we have. Now let's think about finding the internal resistance first one, this one here. Now if you look here, if I take loop number one, this loop here, I start here and then I go around and I come back to the same point here. That means what? That means at this point here, the sum of the voltage is equal to 0. So the sum of V is equal to 0. And that will be, if I do that, then I have 12, right, minus IR, right, because I is not known, IR, right, and then I have minus this one here, minus 2 times 3, okay, is equal to 0, and this equation here will give me, I have two unknowns here, right? So I still need another equation so that I can get from it either I or R. Now, what happens if I apply just this here, loop number 2? Again, I'm going to start here, or let's start at A here. Start A, and then I'm going to say, okay, now this I'm going from positive to negative, so that means it's minus this guy here. And then remember, I'm going against the motion, so that will be plus 1 times 1. Okay, because that's 1, this is 1. And then I'm going to go this way. This one is minus 3, right? 3 times 2. 3 times 2 is equal to 6. Okay. So now, 3 times 2 is equal to 6 is equal to 0. Okay. Now from here, 3 times 2 is equal to, so this is minus. It goes the other way. So E, my E, is equal to minus 6, plus 6, but I have a minus here. So it's equal to minus 6. And remember, because these guys are in parallel, so that means the voltage across here is equal to the voltage across here is equal to the voltage across here. In fact, I can just simply find the voltage here. 3 times 2 is 6. That means the voltage across these 2 points is 6, and the voltage across these 2 points is 6. If I know that, then I can solve the rest of the... I'll leave the rest to you, and then we'll talk about it again tomorrow. Okay, so now this is very similar to the first one, so I'll leave that also to you for you to do it. Now this one is a little bit not challenging, but it's a little bit, let's say, interesting. Okay, so first of all, he wants you to find the current in each resistance and the equivalent resistance. Now, in such cases, we have to apply the two Kirchhoff rules. Because what we want I1, I2, and I3. These are the currents that we don't have. We have I1, we don't know it. I2, we don't know it. And this one, we'll call it I3. Right? This is I3, which is simply, if I use the junction rule, I3 is in. This is out, this is out, so the I3 is equal to I2 plus I1, and that's what he has here. This is simply I3. Okay, so let's call it I3, and then we will know it. So that means I need 3 unknowns. Now, in order to get to solve for these 3 unknowns, I need 3 equations. So I can use my closed loop 1 to get one equation, which is simply going to be what? Is going to be 13 minus, right, and I1 times 1, okay, I1 times 1, and then minus I1 minus I3, because that's my closed loop, I1 minus I3, okay, so minus I1 minus I3, I can't write very quickly here, but okay, is equal to 0. Okay, that's equation number 1. Equation number 2, I can take loop 2. Loop 2, it will be again 13, right? And I'm going to go this one, so it's this one, which is again minus, so minus I2, 13, minus I2, and then minus I3 plus minus 2 multiplied by I2 plus I3. I2 plus I3, right, is equal to 0, right? That's 2 equations. The third equation, so that's loop number 1. I can take this loop here, number 3. I can take this loop, and again I get from it another equation, and then I can solve 3 equations in 3 unknown. So that's another one. So okay, so I'll leave that, and then let's, for the RC circuits, we'll do them in class. So I'll conclude by here. So I'm giving you what I did here. I gave you sort of an overall idea that will support what you're going to read in the PDF file, which I'm going to send you in the email as well. So I'll stop here, and then we'll carry on with this tomorrow, and inshallah you'll enjoy the lesson. This is very important. This section here, what we're doing, this chapter is very important, and in fact, you will have one complete question, something similar to this in the exam on Thursday, inshallah. So I'll stop here and see you tomorrow, inshallah.